Thank you for all coming. Today we're going to be talking about Linux kernel exploitation. But beforehand, I want to start this presentation a little bit non-traditionally. Thanks
To the video.
Okay.
Otherwise, we don't need audio.
You need to get this on recording too. One of my good friends recently had a tragic accident, and I'm of course speaking of my friend, the volcano Ejafalahalakol. I don't know how to pronounce that, but this is a poem that's a tribute and also a warning. It's enough to drive an IT guy quite manic that computing's integrity ends in something volcanic. The gnashing of teeth, waiting for the big crash, is anticlimactic when you're buried in ash. You worry about buffers in C, Perl, and Java, to all be but undone by some freaking hot lava. Some worry about worms, viri, a bot. They think that an outbreak of Zeus makes things hot. Nay, my friend, do not fear, that won't end your day. Behold, we present Cyber Pompeii. Now, I can't actually take any credit for that. That was a poem written by Chris Hoff, who I'm sure tomorrow will have an equally epic intro for his presentation because he is a great poet. He came up with this in literally 5 minutes. But, you know, Cyber Pompeii is something we seriously need to be concerned about as security professionals. So let's get on to the main event here. My name is Jon Oberheide. I did a whole bunch of security research when I was at the University of Michigan doing my bachelor's, master's, and PhD. Now I'm working at Cybersecurity, which is a small startup based out of Ann Arbor working on some strong auth technologies. But what we're going to be talking about today is Linux kernel security. So the question on your mind should be, why the Linux kernel? What's important about the Linux kernel? Why does it apply to you? Why does it apply to everyone in this room? Now, if you're an administrator, I think that's the most obvious approach, is you need to know your exposure rate. You need to know what sort of threats your machines may face if you have Linux-based servers. And also, if you're a researcher, you should understand that there's a lot of interesting opportunities for vulnerability development, exploitation. The kernel is a fairly fertile ground for developing some really interesting exploits. And in kernel space, a lot of the security mechanisms that we've come to love from user space are unfortunately not commonly deployed. We have a lot of mechanisms that you can add on, but they're not in the mainline kernel, and they tend to be relatively immature in terms of their protection capabilities. And the reason why they're not in mainline is because the execution overhead, while might be acceptable for some of your user space applications that aren't as performance critical, of course any code that's going to be in hot code paths in the kernel is going to be very sensitive to any sort of execution overhead, which many of these protection mechanisms may impose. So the title of this talk relates back to the pony that Linus and I think Linux in general won last year at the Black Hat and DEF CON conference. I think there was multiple ponies. One was lamest vendor response, which was a clinch for Linux last year. I think they also, one of the UDEV bugs, which was essentially universal across all distributions, across all versions, Linux privilege escalation, won for best local bug. So if you look at this quote here, there's a few key items here. This is a quote from Linus talking about, on LKML, talking about how normal bugs are way more important than security bugs, simply because there's more normal bugs than security bugs. So from a security perspective, that's absolutely bonkers. A bug that has an impact on the availability or the confidentiality or the integrity of your system is way more important than, say, a random driver bug that will crash under some very obscure circumstances. So this is sort of what you have to deal with when it comes to the upstream kernel. So Linus's stance on this essentially pushes all of the responsibility of kernel security onto the distributions, which really distributions are the ones who are in charge of packaging the kernel, in charge of supporting the kernel, in charge of patching it. So they really should be in charge of the security of it. But on the downside, there's this big disconnect between the developers who are working on the mainline version of the kernel and the distributions who are the ones who are actually packaging this up. So there's developers that might actually be committing fixes for bugs who don't actually understand the security impact of the bugs. And it often leads to this misclassification of bugs. It's not that everyone is bad, though. A couple guys, in particular, Eugene from Red Hat, is doing a really good job trying to chase down all of these random kernel bugs and monitoring the stream and commit stream of fixes to see if really pull out the ones that have security impact. One thing to note here that isn't in this quote was, I think it was in the following paragraph in this email, when Linus referred to all of the OpenBSD developers as masturbating monkeys, which was fairly humorous. I don't know if we have to cut that from the video feed. Maybe we can PG it out with a different name, pleasuring primates maybe. Either way, it's a good Ubuntu release name in the future, I think. I think they have to use one of those. So this bug misclassification is a big problem, where a lot of these bugs are actually not even understood by the developer who maintains that particular piece of code, doesn't understand the security impact, and the people who are looking for bugs that may have a security impact don't actually understand that piece of code. So the end result is that these bugs are often silently fixed in the upstream kernel. Now, I don't mean silently fixed in a malicious way, like they're trying to hide these security issues. It's just a lack of misunderstanding. So there's really no way to know if people are intentionally embargoing these bugs or if they just don't know any better. And this miscommunication is where the attackers can slip in, because they often have a better idea of what conditions are exploitable and have sort of the best from both worlds. They understand the code like the developers, but they understand the security like the distributions are supposed to. So attackers can actually snarf a lot of these bugs off before they're even realized that they're exploitable or may have some other kind of security impact. So another reason you should care about Linux security is mobile devices, of course. My mobile phone right here, Android, and your Droid over there. They run Android operating system, which is a Linux-based mobile distribution. And there's also a lot more coming out. We saw Chris talk yesterday about WebOS and a lot of the problems and how they could actually write a camera image to dev kmem directly through some of their tricks. So a lot of these new platforms like Bada from Samsung and the new one coming out of Intel from Migo are all going to be Linux-based as well. So it'll be interesting to see how they structure their platform. There's really no reason why these mobile devices should not be the most locked down Linux devices out there. The platform designers got to start from scratch. They got to throw all the assumptions out, all the compatibility issues out, and start fresh. And yet a lot of these phones still have sort of the exploitability of like a 1990s machine, where they're lacking all of the modern protection mechanisms against common memory corruption vulnerabilities. And to top it off, you can't actually patch this yourself. So if you know about kernel vulnerabilities, the only way to patch it would be to root your phone and actually apply the patches yourself. There's this large window between when providers will be able to pick up these patches and actually push out these OTA updates, which are much more difficult and go through much more QA than maybe your traditional distribution would release to an enterprise server. And lastly, these phones essentially are multi-user systems where all of the users are these potentially untrusted users or applications. So every time you install an app on Android, it's installed as a different UID and GID, which means that these apps can essentially just sit around. They can a malicious party can develop an app that looks like a game or an application. It can perform its usual functionality, and maybe once in a while it queries off to the network to see if there's a new exploit available. And as soon as an exploit comes around, the app is just sort of a sleeper app. The attacker can post the exploit, the phone will query out, get the exploit, download it instantly and execute it, and rootkit the phone way faster than T-Mobile can actually notice and apply and push out over the air and update against for these kernel devices. So it's very easy to win this race, and it's a pretty serious threat when it comes to these unprotected mobile devices. Also, there have been some privilege escalations for Android. Android Hackers Inc. ported one of Spender's no pointer dereferences, which we'll be talking about a little bit later, to the ARM platform and to Android. Android didn't have any sort of restrictions on where you can mmap memory, so it was very easy to trigger this null function pointer dereference and achieve root. And of course, the phone also didn't have some of the common protections for protecting against rootkits. You would want to disable livable memories and disable devmem, devkmem, but none of this was actually done on the Android platform. The other side of embedded platforms, which I think is pretty cool, is the TVs. So my LG TV actually runs Linux. When I got the TV, I opened up the box and there was a CD in it that said like GPL source code, and I was like, wait, what? My TV's running Linux now? So playing around with it a little bit, turns out it's just actually a MIPS box running that version of the Linux kernel there, 2626, and it's a Monte Vista distribution. They do some real-time Linux kernels. And essentially, you can just plug in your USB thumb drive to the side thing, which is normally used for viewing music and viewing pictures. But instead, you can actually just flash a new firmware onto the TV, completely, either DOSing the TV to make it very hard to recover from, or I don't know. I'm sure you can think of some pretty clever things you could permanently write to the frame buffer on your friend's TV. Alternately, you can just plug in the serial back and pop out a root shell if you have the time for that. So while these attacks aren't that sexy, you have to be at your friend's house and wait for you until it goes to the bathroom to ruin his TV. A lot of the newer models are coming with Ethernet and Wi-Fi, which just makes them another network-connected Linux box, which of course will probably have the worst patch management ever, since you don't think LG has a full-time kernel team working to push out security updates for these devices. And lastly, which I think is the most important reason that you should care about Linux kernel security, is that memory corruption is boring. I don't mean to offend all of you guys in the audience, but it's getting hard. And doesn't mean we shouldn't work on it because it's hard, but if you have a modern Linux distribution with all of your protections, NX, SLR, PIE, RLRO with canaries, exploiting that is going to be very difficult. And there's a lot of non-traditional memory corruption vulnerabilities that are pretty interesting in their exploitation vectors. We've seen, it's not only kernel space. There's some in user space. Like I thought the UDEV vuln from last year was pretty awesome in terms of the various creative methods you could use to exploit it. There were some straightforward ones, but there were ones that were a lot more fun. But in general, there tends to be a lot more of these non-traditional vulnerabilities in kernel space than there does in user space, simply due to the complexity of the various subsystems of the kernel. And it might require you to actually know a significant amount about a particular subsystem, which makes for at least an engaging vuln dev experience, but at the same time, these aren't the same sort of exploit patterns that you're going to apply over and over to like you would with a certain class of bugs. So it's interesting, but at the same time, it might not be as reusable as some exploitation techniques. But if we actually look at some of the local privilege escalations in the past year or so, over 60% of them were not traditional stack and memory corruption vulnerabilities. So a lot of the serious bugs in the Linux kernel do fall into this category of these logic bugs or these non-traditional vulnerabilities that we think are pretty interesting. So if we put it out on the scale of cyber war to cyber Pompeii, I guess you could say, I would rank kernel vulnerabilities definitely above user space vulnerabilities and just slightly above squirrels. I hope Hoff isn't here because he will kill me if he is. No, it's good. I probably butchered his poem too. So before we go forward talking about some of the vulnerability classes in the Linux kernel, it helps to go back and see where we've been in say the past 10 years because that seemed like a good number. So if we look at the number of vulnerabilities in the Linux kernel dating back to 2000 to 2009, we see that they are significant in their quantity. You can see some anomalies in 2005. There was a big spike around there. Actually, in 2005 was the first release of 2005 was the 2.6.11 kernel, and it was when developers and also security researchers really started switching over to 2.6 and adopting and started looking at it a lot closer. It's when they started the new stable versioning scheme where you have a minor and a micro version number x.y after 2.6. But the security gods are not without irony. Linus's announcement email for 2.6.11 said it's now officially all bug-free, which if you look at the graph, obviously it was very bug-riddled as opposed to bug-free. But it's more interesting to actually break this down into the severity of these vulnerabilities since not all vulnerabilities are created equal. And we can see that the spike in 2005, even 2006 a little bit, was mostly low severity vulnerabilities as scored by the CVSS scores in NVD and CVE databases. And more importantly, we see that in 2008 and 2009, we see this growing number of high severity vulnerabilities, which are really the ones you mostly care about. Sure, there might be local denial of service vulnerabilities where an unprivileged user can crash your system, but really that's only going to affect you if you have untrusted users that are just heckling you, maybe in a university setting. And also, the common response is, well, kernels get bigger over time. They have a bigger attack surface, and they grow in code size. So of course, if there's more code, there's going to be more vulnerabilities. So we can actually normalize these vulnerabilities by the number of lines of code added to the kernel over these years. And we see that even when they are normalized, 2009 was still definitely the worst year of Linux security. So the Pony Award was not unfounded and was not based solely on Linus's rants. Of course, it's important to compare to other operating systems too, just to ground ourselves. We see that Linux kernel does have a good number of vulnerabilities, but how are other operating systems doing? How is kernel security going in a broader sense? If you look at these other operating systems like Windows or OS X, their kernel bugs are pretty small and dominated compared to the Linux bugs, both in the medium ones for 2009 and the high severity ones for 2009. And that, of course, makes for a very, very sad operating system. And even worse, it means that the Linux kernel averaged over 2 vulnerabilities a week for all of 2009. So when we're talking about these devices, especially embedded devices, that are going to have fairly difficult QA and patch management cycles, 2 vulnerabilities a week is a lot for a company who doesn't specialize in Linux development to keep up with all these patches. So we're going to move on to some of the vulnerability classes in the Linux kernel. Of course, most exploits can be broken down into both remote exploits and local exploits. Remote ones are fairly rare, but there are some exceptions, and they tend to be very spectacular exceptions. Recently, last year, there was the SCTP Houdini exploit from Skuraku, which was pretty cool. It was SCTP is a transport protocol, similar to balances out TCP and UDP features in a more flexible format. But it is not that commonly used, but it is used by telecoms frequently. So if you did have an SCTP server listening on your network, the SCTP stack, which was relatively new in the kernel, was vulnerable to a remote overflow and a remote compromise via a kmalloc overflow. And it's a pretty involved exploit, but you should definitely check it out because it is some great code. Also, Julian had a Mad Wi-Fi one a couple years back, which is a wireless driver for Linux, which is also pretty neat. It was a stack smashing attack. One thing that's interesting about these remote attacks is you essentially have 2 exploitation contexts in the Linux kernel. Your exploit's either coming from locally, which means it's probably going to be in a syscall handler, where a local application makes a call into the kernel to process some application, and there's vulnerable routines in that particular kernel handler. Or it's going to be coming remotely from a hardware interrupt-based context, which is most of the time these remote exploits where you'll have a device driver receiving an incoming packet and processing it somehow and causing corruption. So actually going from a interrupt context and sort of stepping down into a actual syscall context and getting a shell to spawn back is a pretty complex issue. And those exploits have some pretty cool techniques for dealing with that. Of course, the ones we're going to be mostly concerned about are local exploits, since they tend to be quite common, and they mostly are in the form of privilege escalation, although we'll discuss some potential memory disclosures as well, which can aid in other attacks. And these local exploits are generally the cause of this large attack surface that the kernel has. If you think of a kernel, you might just think of, okay, there's a syscall interface, and all the kernel does is abstract away the hardware from user space. But in actuality, there's a whole lot of different areas that are commonly exploited by attackers. If we look around the circle here, these are probably the most common areas. You have your traditional system calls, which tend to be these passing data back and forth. IO cuddles are set and get socket options, where parameters to these might not be sanitized, so you can either send a lot of memory or copy a lot of memory into kernel space and have it overflow buffer, or you can actually get a lot of memory from an unsanitized length and have it leaked back to user space. A more interesting area is the memory management subsystem, which we'll talk about a little bit later, where we can actually desynchronize what the memory management system thinks is the state of the physical memory and page table entries from what they actually are, thereby tricking it into allowing us to write to some pages that we're normally not allowed to write to. There's the architecture section, which often has, of course, architecture-specific vulnerabilities. KVM has suffered a huge rash of vulnerabilities, even though it's now officially Red Hat's officially blessed virtualization software as opposed to Xen. And there's also been some interesting vulnerabilities in the 32-bit compatibility. Chris Evans had a neat one where you could evade any sort of system call auditing framework by, I think it was calling out to 32-bit syscalls from a 64-bit process, bypassing some of the protections there. There's character devices, there's file systems, both virtual file systems, a format of binaries like your L for A.out. There's network file systems, there's local file systems. There's network drivers like the SCTP that we talked about. The Wi-Fi framework of Mac 802.11 is a recent addition to the Linux kernel. So there's been a handful of remote denial of service attacks against the Wi-Fi framework. None of them exploitable for execution of code, but they were some null pointer references remotely triggerable. And then, of course, you have your device drivers, which are come and go once in a while. The Mad Wi-Fi, the one that Julian wrote, and more recently there was a E1000 vulnerability that you could actually, there's both a local and remote one. The remote was a denial of service, but the local one you could actually write arbitrary data into the card's NVRAM, essentially creating a NIC rootkit, which I was expecting to see in those NIC rootkit presentations in CASEC West, but apparently no one covered that one. And contrary to popular belief, or at least in academia, people think that these vulnerabilities or these flaws are most commonly in device drivers, and really they're not. The device drivers are maybe serious ones because they can potentially be remote, but there's a lot of complexity in the kernel that is not as part of a device driver. So we want to start with a recent example, something fresh. Maybe it was released a week ago or so. There's a vulnerability in the RiserFS file system where Riser has this sort of top-level private directory called RiserFS priv, and the files beneath this can be written by an unprivileged user. It fails to enforce the permissions that it's supposed to, and this is a virtual path. So even if you run RiserFS, you've probably never seen this path because it won't even show if you do a ls-a. This is used for internal file system usage. One of the main users of this virtual path is extended attribute support. So extended attributes can be used for many reasons. Essentially, it was designed to deal with some of the shortcomings of your standard Unix stat structures, where you have your A time, M time, C time. You have your permission bits and your owner bits. So they really wanted something that could be extended without having to change the interface between the kernel and user space via stat every time. So these are just named attributes that can have any name and any value. But the root cause here, or the root result, is that we can actually write extended attributes for arbitrary files on the RiserFS file system. So, how do we actually escalate our privileges by writing these arbitrary extended attributes? One key use, which may be interesting, is the POSIX file capabilities, which allow you to specify more fine-grained privileges than simply setting the setuid bit on a particular binary. So instead of having your ping as setuid, which ping's been pretty audited pretty hard over the years, but there used to be a lot more vulnerabilities in these setuid programs. And now we can actually take away that setuid bit and just assign it one particular capability that's necessary. So ping, since it just opens up ICMP raw socket to send out these ICMP echo requests, can just have the capnet raw. And capnet raw allows it to open raw sockets and nothing else. So we can kind of limit the attack surface of our system and of our collection of setuid binaries by using these capabilities. And these capabilities are stored as extended attributes in the file system. So this mechanism that's actually used to protect the system and make it more secure, we're going to leverage for our own exploit. And one of the capabilities, cap setuid, and it sounds pretty good for a candidate way to escalate our privileges. So what we can do is compile our own shell and throw it in a certain path within the RiserFS file system and attempt to set the capability for that particular file. Now, one of the roadblocks we run into is we don't actually know the inode or the object ID of this shell we've created. The object ID is the internal identifier that RiserFS uses. It's equivalent to an inode. And this is necessary because we need to know what path to write in the RiserFS priv directory in order to put our capabilities in the correct place. So we do a little trick where we can just compile the shell, get a list of the directory entries of that directory, sort of a pre-snapshot. We can set a dummy extended attribute as an unprivileged user, and then get another directory listing of that directory and see the change that has happened, and notice that the new entry in that is the inode of our shell. So we're going to go ahead and do a quick and hopefully painless demo against a fully patched Ubuntu system. Notice this isn't in a VM or anything. I'm actually exploiting my laptop, which is still vulnerable to this this attack. But it's a quick Python script. It's maybe like 50 lines. Not a big deal. Latest kernel. We can see that we're an unprivileged user, and we run our stuff, and we are now root on our system. And to celebrate, we have a ASCII animated volcano, which previously when we were talking in here, we were trying to Google for ASCII volcano art, and there is a huge lack of ASCII volcano art on the internet. So if you're looking for a new startup idea, I highly suggest it's a niche market. But as we can see in here, we see that we found our object in here, and we have our dummy attribute user.hacks in there, and we also have our capabilities, which really won't look like much to you. It's just an encoding of the proper capabilities for cap ZUID. We just compiled our shell in here, and we've given this file, this shell right here, the ZUID capability, so that when it's executed, we are a root user. So, what's interesting here? There's absolutely no memory corruption, not a lot of fancy technique. It's a pretty straightforward exploit, and it just required a little bit of knowledge about the RiserFS file system, a little bit about the extended attributes, and a little bit about Linux capabilities to sort of piece together this exploit, which makes it not really useful for applying to future exploits in most cases, since this isn't really a bug class. It's a one-off exploit. Due to some of these missteps of the logic checking conditions in the RiserFS file system. And this is really representative of a lot of the Linux kernel vulnerabilities that we see. As I said, 60% of them that we saw weren't your traditional memory corruption and were more like this vulnerability. But we also have the standard classes too, which we're going to go through hopefully quickly and chat about. So smashing a stack in the kernel is really no different than smashing a stack in userland. You have a per process kernel stack, which is either 4K or 8K in kernel memory. And we do have existing protection mechanisms built into our compilers, such as stack canaries and bounds checking, which have been applied fairly effectively in user space. But how effective are these same protection mechanisms in kernel space? So one of the things we looked at was the coverage of the fortify source feature of GCC. And fortify source does compile time bounds checking on some of these operations like strcpy or memcopy or sprnf, things that may potentially overflow a static buffer on the kernel stack. And this is actually accomplished through this built-in function called built-in object size, which is a feature of GCC. And if you see here, we've redefined the macro for this built-in object size to return some different values rather than actually doing any sort of verification, just so we can actually count how many times it fails and how many times it succeeds. Built-in object size won't enforce these checkings if it can't get a good idea of what the parameters to these unsafe functions are. If it detects there might be any sort of side effect, it boots out rather than generating potentially incorrect code. So if we do a make yes all yes config, which enables all the kernel options, and run make, we can see that 5,700 times. Do I have those? I have those backwards. Okay, so it actually failed 1,100 times and only succeeded 5,725 times. That's what I get for mocking up fake terminal text there. So the coverage of the fortify source option is actually only 32.9%, which is fairly poor, and it's mostly due to some of the how these buffers are located in various structures in the kernel as compared to user space, where things are mostly just on a stack and not within a struct itself. And actually, a spender has helped out with fixing this and submitting some patches, or at least some knowledge upstream to the GCC developers, so that the built-in object size will be more effective in the future, not only for kernel but also for user space too. So we should hopefully see this, increasing as time goes on. Also, you have kernel heap overflows. In the Linux kernel, you have 3 types of allocators, which are all very similar. Some are just targeted at slightly different allocation models. You have the slab, slub, and slob allocators, and I think there's one more too that was recently developed. Slub is the one that's used by default on these kernels. It used to be slab, but they transitioned over to slub, and it provides the kmalloc, k-free family of functions. And we could spend an entire talk talking about the intricate details of these allocators. Larry H. in Frac66 wrote an awesome article essentially summarizing, 66 was pretty recent too, so it was essentially summarizing the history of all the allocators and going through the various exploitation conditions, which are pretty standard if you are used to exploiting a heap unsafe unlinking vulnerabilities. Now there is Kern Heap, which was just released a few months ago, which is a heap production from the guys at Subreption, also Larry, which provides this metadata protection, safe unlinking, protection against double freeze, checking of uninitialized memory usage, a lot of different functionality that can harden your kernel against these heap-based overflows. The one that people have gotten way overly excited about in the past maybe year or so is these null pointer to references. And calling it null pointer to references is actually wrong. Well, it's not wrong, it's just not completely accurate. These are userland pointer to references, of which null is just a very specific case. Just happens to be the address 0 as opposed to the address 20 or the address 25. And it just happens to be that these null pointer to references happen due to the common programming mistakes you make in a C or C++ based language, and the ones where you might be dereferencing a pointer somewhere else in the userland address space, is not as common as a programming mistake. But in these shared VM architectures, you can see that in your virtual memory space, your user address space is shared with the kernel space. So the kernel sits at the top or the bottom, however you rotate it, of the address space, and is protected from being accessed or modified by the user address space with its page permissions. But what can happen is when you call into the user space code, if you can trick user space functions into dereferencing a pointer into your user address space, and you control the data at that pointer, you can do some interesting things. So traditionally, this is done with a function pointer to reference, where the kernel will attempt to call a function located at a address that's controlled by user space, which essentially you put your shellcode there, and it will jump to there and execute your code with the permissions of the kernel. Or in less common cases, you'll have data control, where the kernel will dereference maybe during an assignment to a pointer in user space, and you'll later be able to control maybe an arbitrary write or some other method of elevating your privilege from that initial data control. So the traditional pattern goes like this. If you have a null pointer to reference of a file pointer, you would set up your payload, you mmap the null page into your address space. Normally, if there was a dereference of a null pointer, it would be an illegal operation, of course, a segmentation fault. But in this case, we're making the 0 address valid. So any memory that's dereferenced there is just like a normal memory access. And we can copy our payload to that 0 address. We do whatever we need to trigger the null dereference. In this case, this is the famous sock send page example, which is triggered with the a send file. And then when the null dereference function pointer is actually dereferenced, it will call into your shellcode at address 0. Your shellcode would then walk the credential structures of the kernel memory and maybe change your UID to 0 or whatever other payload you want to execute. And if you want to look at exactly how easy it is to write one of these vulnerabilities, you should look at Spender's Enlightenment framework, which really you just fill in two functions, sort of a prepare function for before the exploit, and then a trigger exploit, or trigger function to actually cause the node to reference, and then it will execute its own built-in payloads, which are all cross-platform and disable every single security mechanism in the kernel as possible. So what I'm going to talk about right now is actually an example from OpenBSD, which I realize is completely cheating and betraying my talk title. But I like this one because it was multi-stage and had some cute tweaks about it. The git sock op call for OpenBSD's standard IP sockets had an issue where we could eventually get a controlled write of just the value 1 at an arbitrary address. So you might not be clear from this code output here, but this macro actually was expanding to a null to reference and then writing a 1 to a particular address under our control. So breaking down the exploit, how we would actually leverage this into a privilege escalation, we would call mmap to map our 0 page. The kernel would go ahead and map that. We would set up a fake mbuff, which was the structure here that's being operated on in this git sock opt code. We would set this up with a fake mbuff at the null pointer, such that one of the offsets, which is the data member of this mbuff structure, would contain the address of a memory address that we want to write to. So in this case, we can pick a system call table entry, which are predictable and static on OpenBSD. Next, we actually want to trigger this vulnerability with the git sock opt, which causes the kernel to access this fake mbuff located at 0. It has no idea that this is actually an mbuff that was created by a user. It thinks that it's just a normal part of its kernel memory. And it looks at the address stored in our data field and writes a value of 1 to a syscall entry in the syscall table. Now, what's special about 1? How can we leverage that into actual privilege escalation? Of course, 1 is no different than any other address. We already have the 1 address mmapped from our original mmapping of the 0 page. So all we need to do now is just copy our shellcode to the address 1, and then call the system call that we overwrote in the system call table here, which is now pointing at the address 1. And the kernel will dereference the system call, pop over to 1, and execute our shellcode, which is located there, which will then traverse the credential structure and set our process to UID 0. So it's a little extra couple hops than a traditional null pointer to reference, but I thought it was interesting and worth sharing, even though it was OpenBSD. So there's a couple different protection mechanisms to stop these type of userland dereferences. The one that is targeted at this rash of null pointer dereference vulnerabilities is the mmap min-adder support, which just basically disallows you from mmapping to any addresses that is lower than this value. So essentially, if it's set to, say, 4096, we can't actually map anything below that. We can't map the null page, therefore preventing a lot of these attacks from being exploitable. They still are denial of service conditions, but we can't actually hijack the control flow of the kernel. Now this blocks, of course, all the null pointer dereferences, but not all user dereferences, and in fact has been defeated multiple times by Tavis and Julian via a couple different mechanisms here, which were able to bypass this protection, since there are several code paths which allow you to map pages from user space that don't necessarily go through the same code paths that are protected by this mmap min-adder. The more comprehensive solution for these user space dereferences is called udref, appropriately, which is part of Spender's GR security patch set. And on i36, it uses segmentation to enforce these boundaries between kernel space and user space and catch these null pointer dereferences. And actually, just a week or two ago, him and Pipax released support for 64-bit, which is a little more difficult due to the lack of some of these segmentation features that were discarded on the AMD 64 architecture. But it does protect against some of the most common scenarios of these user space dereferences. Of course, there's also things that don't necessarily result in actual privilege escalation immediately. Memory disclosure is one of the, I'd say, underrated bug classes in the Linux kernel. What we can do is actually leak sensitive kernel memory back to user space, and this is most commonly done with a unbounded copy to user operation, which is in charge of taking memory from kernel space and copying it, hopefully safely, to user space. And of course, you can pair this up with a setuid exploit. I had a setuid exploit for this setuid binary called libvirt proxy, which was on Xen-based Red Hat boxes, which would essentially launch and sit there, wait for you to send it some commands, and then had a stack-based overflow, which was perfect for this scenario, since we could launch the libvirt proxy, run our kernel leak, and try to leak out enough information from the task struct or other VMA information in the kernel to be able to bypass the ASLR. My exploit only worked on 32-bit simply because it just brute forced its way through the address space and ran it a bunch of times and eventually succeeded. But you could exploit this pretty easily on 64-bit by leaking information about where the stack base was located. And you can actually, similar to user space, pair up an information leak with another exploit targeting the kernel. The stack canary value from the config cc stack protector protections is located in the task struct, which may be able to be leaked through some of these memory disclosures. Some of the memory disclosures are very small, such that you have maybe a statically allocated structure on the stack, and you fill in a couple values and then sort of copy to user back that entire struct. And due to paddings of the compiler, there might be a few holes in the struct of padding or uninitialized information which can be leaked back. But sometimes we have great ones that, for example, this SCTP, again, another vulnerability in the SCPT subsystem, in the git sock option, which was also where the OpenBSD one was in git sock op. These are very common areas, where we actually control the length value coming into this function here. And as you can see, the length value is, they make sure that it's not too small, but they don't make sure it's too big. So you pass in this length value with your git sock opt, and what it will do is copy back pretty much an arbitrary amount of memory, kernel memory, back to user space through this last copy to user here, taking in the length value. It's only meaning to copy this very small structure of the HMAC values, but in actuality, you can leak a whole lot of kernel memory. Race conditions, I'm getting pretty late on time. Maybe we'll skip through that. There's some great work trying to exploit these on uniprocessor machines, where you can actually force the kernel to sleep or reschedule processes in certain code paths. But of course, if you're on SMP, you can easily exploit these by having multiple threads in a race condition. This is a very simple example showing that a length value was copied from user space with this get user function. It went through a sanity check, but then later in that function, they actually recopied the length value from user space without actually doing any validation. So even though it was copying the same memory address in both of these get user calls, there's this window of time where we would actually be able to race and change the value that is trying to retrieve here in between these two get user calls. So it can pass the validation in step 3. We can change it. It will copy in the new malicious value, and then it will do a copy from user with this malicious length value, allowing us to overflow. I think this was a kmalloc buffer. And last, there's these great bugs in the memory manager. The memory manager is a very complex system which is essentially in charge of bookkeeping all of the state, all of the various VMAs, all of the protection flags, and it does some complex splitting and merging of these various VMAs that can be desynchronized from what the actual state is in memory. And if you guys follow the PS3 hack, the George Hotz guy did this with the OS and hypervisor, where he was able to do a lot of allocations and deallocations and actually able to desynchronize the state of the memory manager from what was actually in physical memory based on actually glitching the memory bus while these memory mappings were happening. So he actually had physical access to the PS3 and was glitching the physical bus line on the PS3. Now we can do the same thing for the kernel but instead of actually glitching the bus on our machine, we're just sort of taking advantage of a bug that throws off the bookkeeping of the So there's some really awesome exploits from the guys at isec.pl. These were old, but they're still incredibly awesome. I think they're from 2003 mremap. There's a mremap unmap one, and there was a dbrk which if you look at a very simple explanation of this, we have our user space, which is our virtual address space, which is shared both by the user space and the kernel space. And what we can do with the BRK function call is expand the area of memory that's usually used for the heap. And unfortunately, they didn't actually do proper sanity checking on how far you were expanding this heap. So we could actually expand the heap past where the kernel address space starts and overlap our heap with the kernel address space. And then when we call mprotect to modify the protection, since the kernel address space is protected with the page table permissions, mprotect would say, hey, this memory is part of the heap. I'll go ahead and modify those MMU values for you. So then kernel address space becomes writable by user space, and you can escalate your privilege that way. So we're about out of time. I'm going to wrap up quickly. For researchers, I really encourage everyone to spend a lot more time in kernel space. There's a ton of interesting bugs, interesting vulnerabilities, and interesting exploits. For administrators, a lot of these distributions are very conservative in nature. They will not apply these security features, even if they're available, simply because there can be performance impact, there can be compatibility issues. So if you are really concerned about this, prod your distros to start deploying some of these protection mechanisms. And there's a lot of hardening you can do on your own through these patch sets, which aren't included in mainline, such as GR security packs and the current heap ones that I've mentioned so far today. And you should definitely be sponsoring and supporting these guys who develop these patch sets, because they're the ones who actually have a big impact on Linux kernel security. So last, before I sign off, we released a tool which allows you to audit your kernel config, both from your running kernel or from a kernel config on disk. It's based off this checksec tool from Tobias at TrapKit, which is pretty good for auditing user space stuff. Auditing whether you have NX and RELRO and PIE and everything for your user space binaries. And I've added kernel support so we can check for a whole bunch of commonly forgotten config options which can help harden your kernel against attack, and you can download the patched version there. And the takeaway of this presentation is not to scream about how insecure Linux is. As we all know, security is not a binary state. It's not either secure or not secure. Most of security is trying to deal with this uncertainty and develop some sort of risk management around this uncertainty. I love this quote from Rumsfeld where he says, there are known knowns, there are known unknowns, and there's also unknown unknowns. It's a very jumbled quote, but it actually has some applicability to security, as he says, in each year we discover a few more of these unknowns. So hopefully the unknowns that we discover this year won't be as severe as we saw in 2008 and 2009. But if you prefer a more simple quote, we have G.I. Joe here saying, now you know, and knowing is half the battle. And with that, I'll open up for any questions from you guys. Thanks a lot. No questions?
I have a comment.
All right.
So you showed a comparison of Linux kernel bugs versus Windows and OS X, and I know you weren't implying this necessarily, that it means the kernel is better. It's just that because of the lack of remote access and because of researchers such as yourself and others are concentrating more on these local, kernel exploit issues. It would not surprise me at all to see equivalent issues that are happening within Windows and in other environments that are rough analogs. It just might be that there's more attention, that there are more people paying attention to Linux kernel, perhaps because it's open source.
I agree. I don't know if we can get that on tape, but yes, I agree with that point.
I think I would argue that if that's the case, that more people are paying attention to the Linux kernel, it's because generally compromises in the Windows world mean full system level compromises or admin level compromises. Whereas with Linux, you're generally running as a limited user most of the time. And in Mac OS X, well, nobody's paying attention because we've got a market share there, or a very large one.
And there's actually been a flurry of there's a lot of local denial of service in the last patch Tuesday. And I think there was a one or two local privilege escalations in the Windows kernel recently too. So it's not like they're not found there. I think attackers just concentrate on different goals. On a Linux box, you might want to maintain a better foothold in this environment that might be more monitored by administrators. When on a Windows box, the general Windows user might not be as aware, or you might not need as sophisticated rootkits to hide from that user. So it can be a difference in environments or attackers' incentives and goals.